Great. Thank you, Robert. Well, it's great to be here after a few speakers. I think a lot of the problems have been really well motivated. And I'm really happy to be here at this workshop because I think one of the things we really need in this sort of community of quantum researchers is programming languages people. And it's really exciting to see so many people in this room. As Robert mentioned, I lead this project called EPIC, which is an NSF expedition. And it is, I guess, one of the projects trying to bring together people at all levels of the system stack, from algorithms to programming languages, to compilers, to architects, to technology people. Actually, a few of our EPIC team members are here today, John Reppy and his student Kartik, who will be speaking later today, and my student Yunong Shi. All right. So what I'm going to talk about today actually is we have this really hard problem, which is how to design programming languages and systems for quantum machines, and in particular, how to do things like verify correctness. And then what I'm going to talk about is how to make that problem a lot harder. Okay? And I'm going to motivate why we want that problem a lot harder, so we'll get there. All right. So as been mentioned already, we're at this very exciting time that we have these machines coming online. And they're of a sort of non-trivial size, and so very soon we'll be able to compute things that we can't simulate and that we couldn't compute before, right? So as John Preskill would say, this is a very historic time. But the problem we have is, of course, these machines are not reliable, and it's going to be very difficult to get correct, useful computation out of them. And I think it's been, I think there's this great slide where you have the transistor from the 1950s and the machine and the qubits that we have now and how they're analogous. And really, that's what's exciting, right? It's as if we were alive in the 1950s, or at least researchers in the 1950s, and we're on the ground floor of a new technology. OK. So let me just reiterate the hard problem, right? The hard problem is that we're in this sort of ridiculous bootstrapping situation, right, where we're going to be building machines that we're really pushing the limits and that they barely work, right? And at the same time, we're going to be writing software that has been largely untested, right? And when we run this on the machine, basically we're not going to get the right answer, and we're not going to know which one was wrong, right? So one thing I would say is that there is a little bit of progress in how we're going to debug these machines and simulations of these machines. There's some interesting work from our Princeton group and some follow-on from North Carolina State that's coming up in ASPLOS in March, which is we can have a certain amount of testing which comes from sort of quantum assertions that actually sit in the quantum program. That costs us actually gates and resources, but it's sort of an interesting sort of stopgap measure. But really what we want is we want to use formal methods, which is really what everyone in this room is about in many ways, right? So we'd really like to see more formal methods of showing that our software is nominally correct, so that when we actually run it on hardware, at least we'll know what caused the problem, right? Now, fundamentally, when we talk to our theory group at MIT, there's this really interesting conundrum, which is you can't test anything about the quantum program that is reducible to computing the quantum program. Because if you do that, and you do it in tractable time, you've basically shown that that program is no good, right? Why do it on a quantum machine, right? And so the really interesting fundamental problem is, what things can we test about a quantum machine that are not too close to the answer that you're trying to compute, but actually teach you something about whether the machine is, or whether the software is correct, right? And good examples are things like linear types for no cloning and things, but how can we expand that set of things that will give us some assurance that things will be correct? OK, so that's what we'd like to see. But there's also something else we'd like to see, which is going to make this problem a lot harder, right? And this comes from this notion of, I think as already mentioned, there's a gap between the algorithms that we'd like to run and the machines that we foresee having any time in the near future, right? And that gap is really large, okay? And that's for sort of our famous algorithms, factoring and Grover search. It's not so bad for things that we're focusing on right now. I think Bettina mentioned, problems in quantum chemistry, applications that are going to be exciting in the hopefully near future. But still, you can see that there's a pretty big gap, orders of magnitude still, between what we'd like to do and the machines that we have. And Bettina also mentioned that, we'd like to get here, right? And so, what we're going to do, and that's sort of the project that we're working on, and hopefully other people are working on, is how to close this gap. And the way we're going to do that, right, is we're going to look at this traditional stack of software that there are many instances of already, actually, and we're going to try to, perforate this stack and give ourselves a lot more efficiency, okay? And in fact, we have this pretty ambitious goal, which we call the EPIC goal, which is to make machines 100 to 1,000 times more efficient using the software stack, and by potentially redesigning the devices to some degree, okay? And the significance of that goal is if you look at this progress of machines, even though it's exponential, right? It's about 10 years, 10 to 20 years of progress to get yourself 100 to 1,000x there, right? And so the idea is to get practical computations running on machines 10 to 20 years earlier by being smarter in our software, in our compiler, which has, we'll see, strong implications as to also how you would design the programming language. OK, so let me just be a little bit more precise. So when we, this graph here just has qubits, right, at a log scale on the y-axis. But looking at qubits as a measure of quantum machines is about like looking at clock speed as a measure of microprocessors, right? There's a lot more going on. Just to be a little bit more precise, a very typical measure would be the space-time product, right? So the number of qubits you can run that you support and the number of gates or instructions you can support on a machine before that machine fails. And there are a few other things, of course, but this is a sort of a first-order model. Now, one way you can think of this is, let's say that you can run a 2-qubit gate or instruction with an error rate of 10 to the minus 3, right? 1 in 1,000. That means that if you have 2 qubits, right, you can run 1,000 operations on those 2 qubits before there's an error and your computation is erroneous, right? And if you have 1 qubit, let's say 2,000 qubits, right? Then you can run sort of 1 gate on every pair, and you can't really do much work with those 2,000 qubits. And more usefully, you would probably balance these two a little bit, right? And so you have this little volume here, right, which is 32 and 32. And optimistically, you might get a machine the next, I don't know how many years, right? 4 years, let's say, that has an error rate of 10 to the minus 5. And I think our Google colleagues like to say they're going to get here real soon. This would give you something like 128 qubits and 1,000 gates each, right? And this, we might argue, if we're really smart about our software, we could do something useful with, okay? So when I talk about getting 1,000x better efficiency, what I mean is some combination of number of qubits a program needs, number of gates it needs or instructions, and how much reliability it needs from that computation, okay? So I'm going to give you a few examples which we've had a lot of success with in terms of increasing the efficiency. And they're going to be examples that show you that we really have to cut across the stack and change our model of what the machine looks like. Okay, so the first one is this work on direct-to-pulse compilation, which is essentially taking programs and compiling directly to analog pulses that control the machine. Okay? This appeared in ASPLOS last year. Yunong Shi, who's sitting in the audience, and is also on the market this year for academic jobs, if you want to talk to him more about it. OK, so in this example, what we can look at is, this is on the left side, a very traditional compiler flow, as traditional as the history of quantum computing long history has been. We have some program that goes to some quantum assembly, which is essentially gates, and that's been mentioned a few times already. And then those gates actually don't necessarily match the gates that a real machine supports. So there's some translation from those gates to the gates that your machine supports. And then the gates that the machine supports are actually translated into analog control pulses that actually implement the gates on the devices. All right. Now, because of this sort of mismatch here, we thought, oh, it would be a lot more efficient if we went direct to pulses. All right. Now, this is actually a little bit, in this example, a little bit of a roundabout way. And in fact, hopefully quantum theorists and people in this room will come up with a better way. Okay? What you'd really like is you'd like to take your quantum program, break it up into big pieces, and to give those pieces directly to the pulse generator. Right? In fact, the pulse compilation tool scales exponentially in computational complexity. So you can't give it the whole program. You have to give it little pieces. And it turns out that we don't yet know how to break up quantum programs into pieces larger than 2-qubit and 1-qubit operations in a good way, right? So what we do, and actually sometimes the programs are already written this way anyway, okay? So we get here first, and then we actually group them together into larger groups, and then we give these large groups to the pulse generator, and we give these nice pulses, and it turns out this is like 5 to 10x more efficient, okay? So here's an example. Here's a quantum circuit. We've seen a little bit of this already, right? Inputs on the left, time goes left to right, outputs on the right, right? These things are single qubit gates. These things are 2-qubit gates that cross between. OK, so if we take this, this is actually part of quantum approximate optimization algorithm. If we take this little piece here, and we do it the old way, we're going to generate each gate as a pulse implementation independently and sort of concatenate them here, we get a thing that looks like this. Okay? If instead we give that whole thing to the pulse generator and have the optimizer do it all at once, we get a thing that looks like this. Right? So what you see is much shorter and simpler. Right? And the result, just as a summary, here's a whole bunch of quantum circuits. Right? Each one of these shows you it's normalized in terms of how long that pulse sequence is from the base case, which is the old way, right? 1-qubit and 2-qubit gates translated to pulses. And then we go to more and bigger groups, up to about 5, a maximum of about 10. Once we get to 10 qubits in a group, the optimizer tends to fail, either through computational complexity. Also, it's basically searching a very high-dimensional space through gradient descent, and it gets lost. It doesn't find a good solution, right? But what you see here is you can see that you get pretty substantial speedups, sometimes 5x, sometimes 10x, right, as you go to the right. What's also interesting is you see that the ones on the left here tap out much faster, right? And that's because actually there's a trade-off between parallelism and aggregation. Right? The more we aggregate our dependency graph into supernodes, the more serialization we actually introduce into the computation. So if the application is parallel, we tend to start hurting ourselves, and we don't get much advantage. But the application is serial, then we can sort of afford to do a lot of aggregation, and we get a lot of benefit. All right?
Sorry, what's the meaning of the shaded region?
The shaded region, actually, this is the average. The shaded is the different subcomponents, how much they got. Right? So then, and then the black is the aggregate. OK. So I'm giving you 3 examples in 30 minutes, so it's going to be really fast. What we got out of this is if we break the ISA abstraction, right, we can get 10x to 6x, or 6x average reduction in latency. It was especially useful on the machine we use, which is superconducting cavity machine. It's Dave Schuster's machine at UChicago. And we're looking to run this thing on real machines soon. OK, so that's the first example. Here's another example. Now, this is an example of compiling 2 very specific machines, right? IBM, specific size IBM machines, and actually some Rigetti and ion trap machines in the second paper. And actually compiling to their specific variability and reliability of each device on a particular day. Okay? And this comes from this observation that if you look at, this is calibration data from IBM's machines. They calibrate their machines actually, I think, twice a day. It's published once a day. And this shows that, for example, for different qubits, how reliable are they, right? And what you see is that those different colors are different qubits. You see that they vary quite widely. And they even vary day to day quite widely, right? And so what this suggests is that when you compile to a particular machine, it's important to be aware of the conditions of the qubits that day. And also the conditions of the links between the qubits. These are pairs of qubits. And how reliable is the operation between that pair? Okay? So what you want to do is you want to basically map to the machine and schedule in such a way that you take advantage of the ones that are more reliable and you avoid the ones that are less reliable. And this is a simple example. This thing is one of the basic algorithms, Bernstein-Vazirani, which is essentially reverse engineering a secret key. And you're going from left to right here. You map this thing. This is actually what the IBM native compiler would do, right? It would map this on this machine. I think actually an IBM native compiler now has this. So now the IBM native compiler would do this, okay? Which is it would avoid these X's and those circles, which are the bad qubits. And what we see is that if we compare to the old version of the compiler, to a version that optimizes for communication, let's see, optimized for communication and 1-qubit gates versus optimized for noise and communication and 1-qubit gates, what you get is you get what's called a much higher success rate. And let me explain, when you run on one of these machines, you typically run something like 1,000 trials. You take a histogram of all the results, and you hope that there's a peak where the right answer is, right? And so having a higher success rate is much better for differentiating the correct result for your machine. OK. So this actually got about up a max of 28x better success rate, a mean about 3x, 2.9x. It improves. We can improve the compile time. Actually, one thing I didn't talk about is that it can be expensive to do this optimization. And it was actually run on all 3 of these machines. And it turns out that it was better than all the native compilers. And by the way, one of the things that we find very useful in our project is, as an academic project, it's useful to prototype these techniques and then integrate them back into the tool chains of these machines, because then those companies maintain the tool chain for us, right? OK, whoops. Let's go forward. OK, so one more. OK, so this is an example of basically fundamentally changing how we use the quantum devices, right? Instead of using them as binary qubits, which have been introduced today, we're going to use them as ternary bits, or qubits, OK? And the problem, actually, Bettina very nicely already introduced, is going to be something which is this multi-qubit, multi-control TOEFL. But first, let's talk about this. So the nice thing about quantum devices is they have an infinite spectrum of energies, right? Well, theoretically, anyway, infinite. They have a lot of energy levels. And in fact, we usually just truncate the energy levels and use the first 2 or so in order to get a qubit. The nice thing about this is if you think about qubits or ternary arithmetic in the classical case, right? If you take a classical technology and you try to partition it into more than 2 states, you're basically taking the same, say, voltage range, and you're breaking it up into more pieces, and you're basically playing with your noise margins, right? And so you're taking the same amount of signal, and you're splitting it up more, so you don't have more signal, right? Here, actually, you do have more signal. So there's sort of a fundamentally different trade-off going on here. There are costs. When you go to higher energy states, there's more noise, which we'll talk about. The other cost actually is measuring more than a 2-state system is much harder. So measuring a 3-state system is much harder. It turns out in this work, we actually never measure. We only use the qubits in the middle of the circuit. But in the future, it'll be interesting if people actually use this kind of technique for other kinds of circuits. OK, and so a generalization of this is if we take a bit flip, right? Instead of flipping bits, we can basically increment bits and do it mod D, mod 3 in our case. OK. So the problem we're interested in is this thing, right, which we've seen already. Essentially, what this is this gate happens if these are all true, OK, or some quantum superposition of that condition, OK? And so this can actually be, in this case, we're using X gate, it can actually be any unitary or any one qubit gate. All right. Now, there's an interesting space-time trade-off here, which that's actually what Patino's using for an example. You imagine that you can't actually implement this gate natively. So what you want to do is, if you have a linear number of extra bits, right? So if you have twice as many bits, you can build a log tree and make this thing log depth, right? So you build a tree to reduce all those guys. If you have no extra qubits, or like, if you don't have any ancilla, no extra qubits, then this actually takes linear time. You're basically combining the results one at a time. Okay, and that was that PLanQC circuit. OK, so this is what we do. Instead, we turn it into this thing, right? So what is this thing? This is basically borrowing the third state to essentially simulate that ancilla. Okay, it's not quite, because if you had a Q quart, then it would be exactly that, right? A Q quart, basically, if you had n Q quarts, that's just like having n ancilla and n data qubits, right? This is actually a little bit more efficient than that, so there's a little bit more craziness going on. But essentially, it's a log tree built with these things where it depends on what state you're in, state 1 or state 2, right? That's the control. And we have these modular X gates, essentially. And what does it do? It's really interesting, right? Because you've taken something, you've just given yourself one more state, a little bit more information. You get these ancilla. You actually get a log depth when you would have had a linear depth. So you actually get an asymptotic difference in the gate depth of this circuit. And you get, it's still the same order of a linear number of gates, but the constant is much better. And so this, it's an interesting game, right? And what's interesting is that when you go into the third state, right, there's this trade-off that it's going to be higher error, right? And so here is a model of superconducting qubits and ion qubits, and how does that trade-off come together, right? So you have higher noise, but you have fewer gates, actually. So the depth is lower, which helps you. And so what you see here is for the superconducting circuits, right, this is fidelity, right? It's a little bit like the success rate. And the orange one is the qubit implementation, right? And this is the current IBM parameters. This is 10 times better T1 time. This is 10 times better gate fidelity. This is both 10 times better, right? And so projecting to the future, this gap sort of closes a little bit, right? Because the depth advantage is less. Ions are interesting. They're totally different technology. They're a little bit more reliable under certain metrics, assuming they could build them large enough. And you see that the difference is a little bit less. The stressed qubit is interesting. It's an implementation that uses 4 states to represent three logical levels. OK, so the summary is, we get, depending on how big your circuit is, we get substantial an order of magnitude reduction in number of ancilla you need, right? Gives you better reliability. And we're actually that error model is pretty conservative. We're looking to actually run this on real machines. Actually, we have done this just recently using OpenPulse, which you're going to hear about very soon. Yes, you might be surprised. We did some simple 3-state experiments. You're not actually supposed to be able to do it on OpenPulse. You had to upsample the frequency. But anyway. Oh, yeah. OK. So this is my third example of what can be a really exciting set of optimizations, right? If you sort of expose the sort of physical details of the machines, right? And really the question is, how is that going to affect the stack as we go up? By the way, you should warn me when I get, OK. So now what I'm going to do is talk a little bit more generally about going into the future, what I think where there are going to be some hard problems, and how that's going to affect sort of the PL and compiler and tools stack. OK. So here's an interesting one, which we haven't looked at yet, right? Which is that we have this abstraction that we can do 1 and 2 qubit gates, or maybe even qtrits, right? It turns out that a number of technologies, I didn't put superconductors here. We could do that too, actually. But will give you the ability to do locally global operations or global operations, right? So you could have an operation which affects many gates at once. If you think about ions, right? The ions have basically the basic gate is a global gate, and you basically have to factor it into a single qubit or 2 qubit gate, right? So naturally, if you could compile your program into pieces that take advantage of global operations, that would be great. I think intuitively and from people's experience, that's going to be pretty hard, right? Like you have a program, unless it's already written that way. We have to think about what are the right abstractions to take advantage of something like that. This is a neutral atom array, a little bit like trapped ions, but trapped using optical tweezers, possibly in a 2D array. It turns out that neutral atoms have a variable interaction distance. So you can set that so it's like a 2 qubit gate, or you can set it so it's like 10 qubits in a neighborhood get the same thing, right? So that can be very interesting. And so how can applications use this locally global operation, and how can we structure languages and compilers to deal with that? This is another interesting one. So a lot of the near-term quantum sort of algorithms are essentially energy minimization problems, right? And so you can think of the quantum machine as minimizing energy in a particular set of constraints. And these algorithms, like sort of quantum adiabatic optimization, quantum approximate optimization algorithm, and even quantum chemistry to some degree, are essentially encoding the problem into the physical machine and then relaxing the machine in some way. And you can think of this adiabatic evolution, essentially. You start with a model that the machine is representing, and you initialize it basically in the ground state. So it's basically already in sort of the optimal solution for that. And then you slowly evolve the machine so that it represents the target system you're trying to solve. Okay? And if you do this slowly enough, this little ball, which is where you are, the ground state, doesn't roll out of this minima, right? And so you just slowly evolve this over. And there are a whole bunch of other ways of doing this. But this basically amounts to evolving the system slowly enough in some way. And this is typically done with 2 qubit gates on a digital system. It's also done on the D-Wave machine in an analog way. It turns out that the digital machines can be evolved, some of them, with analog primitives. So you could expose analog machine primitives to your compiler and to your language. The real question is, how would you do that? And more interestingly, how would you mix analog and digital operations? Because the digital operations give you much more controllability and much more flexibility in what you can do, right? We have no idea, actually. I think we proposed this 2 or 3 years ago, but we haven't worked on it yet. But this would be great. If someone has a good idea. How much time do I got? Okay. Other problems we have. We don't have a lot of tools, right? I think actually Microsoft is probably, and IBM to some degree, have made some progress on this to help programmers, right? Debuggers, performance profiling, visualizing what your program is doing. I think these are all going to be pretty interesting things to work on. I'm particularly interested in this idea of program synthesis for generating correct circuits, actually. Here's an interesting visualization. Actually, Yunong made this a while ago, which is, this is HHL, which is the linear systems algorithm, which Aram Harrow was part of. And this shows over time how much entanglement was there in a particular part of that program. Okay? And what I think is interesting about this is that it's sort of middling, right? Which is interesting because it's not everything, but it's not small enough to be trivial either. But I think it's also interesting because this kind of plot might give you some intuition as to whether you implemented your program correctly, right? Because there's some expectation as to how these kinds of resources will proceed. Okay, finally, I'll end with this little more off-the-wall example, right? So if you're familiar, maybe in this community, with this idea of program sketching, right? So you essentially sketch a program in a fairly under-constrained way, and then you have a synthesizer that essentially randomly creates programs and then verifies whether they actually did what you wanted. Then you can synthesize code, right? And there are better ways of doing this. You can have some feedback that makes a synthesizer not random. This is an example that actually Yurnong also made, which is synthesizing quantum teleportation from a sketch. And what's interesting about it is that it's not the kind of program that a human would have made, right? It's not so intuitive, actually. So there are two things about this. One is maybe you can come up with programs that are interesting variations that have some optimization potential. And the other one is that maybe you can do this in a provably correct way. And that might be easier than proving correctness of something that a person wrote, right? Both of those are hard problems. But an under-constrained person writing something gives you a lot of space to have to search to prove something. All right, so let me wrap up. We're in this situation where we have this stack that's been evolving, and we have some set of abstractions. And that's been great because that makes us be able to work together, and we have a community, and we can make progress. But it is the case that in many cases, some of these abstractions are probably a little premature, or at least will need to evolve as we think about how we can make machines more efficient, right? And we can think about this. I showed the gap between algorithms and machines, right? But there's also sort of this gap where you can think of us as working on sort of the short term, right? Where we're in the small number of qubits and the small machines. And sometime we hope to get over here. And this is the same evolution that, of course, we went from the 1950s and classical computing to where we are now. And the question is, how much of what we do here is going to persist as we move to the right, right? It's interesting. I mean, my intuition is that actually a fair bit. Because it actually, at least standing where we are right now, it's hard to imagine we're going to have a future where qubits are free and operations are sort of infinitely reliable, right? So we're always going to have a little bit of this, breaking abstractions, I think. And the question is, how many of those and how far we have to go, right? And what's the trade-off there? What's interesting, of course, is that classical machines are sliding a little backwards now, right? As we have more variability and as we become power constrained as machines get feature sizes get smaller. Okay. So let me end. Let me reiterate, we're at this really historic time. It's super exciting. And I think that we really need help from this community, right, to accelerate the progress that we have and get to practical quantum computation. And we're really, people who sit here from different companies, we really need more people who know about these areas, right, and are more in the upper level of the stack. Okay, and then we actually have quite a lot of resources here in this effort to build this community and actually infrastructure so that people can look into these issues. Thanks a lot.
Thank you so much. We'll take 2 questions.
Dr. Chong, thanks for the talk. I was generally interested. I'm a physicist, not in the field, just curious. I'm trying to get some ideas. So you mentioned topological transformations you would want to achieve. Do you have any interactions with people working on topological insulators, for example? kind of the condensed matter physics community that uses as a means to kind of get a physical realization of dealing with some of these issues. So do you have any interactions there? What is your take on how far that field has progressed to be useful here in the quantum computing community? So could you give us just a general take on that, what your view is, and let's say, how far are they going to be helpful in the next 5 to 10 years?
Yeah, so, I mean, I don't specifically have too much interaction there. I mean, I think that the exciting thing is, I think Bettina stepped out. She's still here? No. I mean, is that Microsoft is particularly interested in topological systems, and they're working on this Majorana qubit, which will give them, if successful, you know, when they get that to be practical, would give you many orders of magnitude better reliability in qubits, right? And so I would characterize their technology effort as sort of a moonshot effort to get to a point at some point which could be substantially better.
Oh, all right, let's thank Fred. And I'll turn it over to Frank, who will be chairing the rest of the session.
You have your